Welcome to our number theory lecture. Today, we are going to explore one of the most fascinating quests in mathematical history, the search for a formula that can reliably generate prime numbers. We will look at two famous attempts by brilliant mathematicians, Pierre de Fermat and Marine Mersenne, and see how their discoveries still shape modern computer science today. Before we dive into the math, let us understand why this matters. For centuries, prime numbers were seen as chaotic and unpredictable. Mathematicians dreamed of building a theoretical machine where you could plug in any whole number and a prime number would always pop out. In the 1600s, Pierre de Fermat thought he had finally invented exactly that. He noticed a specific pattern involving powers of 2 that seemed to consistently produce prime numbers. This brilliant, though ultimately flawed hypothesis led to what we now call Fermat primes. Now that we understand Fermat's goal, let us look at the formula he created. Fermat proposed that you take the number 2, raise it to a power that is itself a power of 2, and then add 1. On screen, you see f sub n equals 2 raised to the power of 2 to the n plus 1. Here, f sub n represents the resulting Fermat number, and n is just a non-negative integer acting as our index, like 0, 1 or 2. Because the exponent itself doubles every time n increases by just 1, these numbers grow astronomically fast. Before we move on, let us see this formula in action with a concrete example. We will test Fermat's hypothesis by calculating the first few numbers in his sequence. We start by plugging in n equals 0. 2 to the power of 0 is 1, so we get 2 to the first power plus 1, which equals 3. 3 is indeed a prime number. Next, we plug in n equals 1. The inner exponent becomes 2 to the first power, which is 2. 2 squared is 4, plus 1 gives us 5. 5 is also prime. So far, the formula works perfectly. Continuing with our calculation, let us test the next index, n equals 2. We substitute 2 into the formula. The inner exponent is 2 squared, which gives us 4. Now we calculate 2 to the fourth power, which is 16. Adding 1 gives us a final answer of 17. 17 is also a prime number. Fermat actually calculated the next two numbers as well, getting 257 and 65,537. Seeing 5 primes in a row, he confidently guessed that every number generated by this formula would be prime forever. This brings us to an important historical turning point. Fermat did not have a calculator, and the next number for n equals 5 was too large to check by hand. A century later, Leonhard Euler tested it. He plugged in n equals 5. The inner exponent, 2 to the fifth, is 32. 2 to the 32nd power plus 1 yields a massive number, over 4 billion. Through brilliant deduction, Euler proved this number can be divided evenly by 641. Because it can be factored, it is a composite number, not a prime. This single calculation shattered Fermat's hypothesis. Now that we have used this formula, let us understand where its specific structure comes from. Why did Fermat insist the exponent itself must be a power of 2? Let us prove why. We want to show that if 2 to the power of k plus 1 is prime, then k cannot have any odd factors. We will use proof by contradiction. Imagine k does have an odd factor called a, meaning k equals a times b. We substitute this back in, giving us 2 to the power of a times b plus 1. Using exponent rules, we rewrite this as 2 to the b all raised to the power of a plus 1. We then bring in a standard algebraic identity for the sum of two powers when the outer exponent is odd. Continuing our proof, we apply that algebraic identity. By substituting 2 to the power of b in place of x, we can expand our expression. Look at the right side of the equation. It clearly shows that 2 to the power of b plus 1 perfectly divides our original number. Because it has a factor other than 1 and itself, the original number must be composite. Therefore, to have any hope of being prime, the exponent k cannot have any odd factors at all. The only numbers in existence with absolutely no odd factors are powers of 2. This proves exactly why Fermat designed his formula the way he did. So we have seen Fermat's approach of adding 1. This brings us to a different strategy. Imagine you have a massive stack of coins that doubles every day. If you take away exactly one coin from that pile, you sometimes end up with a prime number of coins. A French monk named Fermat and Mersenne studied this exact pattern in the 17th century. Instead of adding 1 to a power of 2, Mersenne decided to subtract 1. This simple shift in strategy created a completely different family of numbers. As we will see, Mersenne's approach turned out to be incredibly fruitful, and these numbers are still heavily researched today. Let us look at the mathematical form of Mersenne's concept. The formula is m sub p equals 2 raised to the power of p minus 1. Here, m sub p represents the Mersenne number. The symbol p represents the exponent, and for this formula, p must be a prime number itself, like 2, 3, 5 or 7. If the final resulting number, m sub p, also turns out to be prime, it earns the official title of a Mersenne prime. Notice that as the prime exponent p increases, the value of the Mersenne number grows exponentially, making them very large very quickly. Before we analyze the properties of this formula, let us see it with a concrete example. We will calculate the first few Mersenne numbers by plugging in the first prime numbers for p. We start by setting p equals 2. 2 squared is 4, and subtracting 1 gives us 3. Since 3 is prime, it is our first Mersenne prime. Next, we set p equals 3. 2 cubed is 8, and subtracting 1 gives us 7. 7 is also prime, giving us our second Mersenne prime. The formula is working nicely so far. Continuing with our examples, let us test the next prime exponent, which is 5. We plug p equals 5 into the formula. 2 to the 5th power is 32. Subtracting 1 gives us a final answer of 31. The number 31 is prime, making it another Mersenne prime. At this point, it seems like plugging in a prime exponent always guarantees a prime number as the result. But as mathematicians, we must be careful not to make the exact same mistake that Fermat made by assuming a pattern holds forever without proof. This brings us to a crucial counterexample. Let us skip ahead slightly and test the prime exponent 11. We want to see if m subscript 11 is a Mersenne prime. We calculate 2 to the 11th power, which is 2048, and subtract 1. This gives us 2047. At first glance, this might look prime. However, if we test it for divisibility, we find that it is actually the product of 23 and 89. Because it can be factored, it is a composite number. This proves that having a prime exponent is a strict requirement, but it is not a guarantee that the final number will be prime. Now that we have seen that the exponent must be prime, let us understand why mathematically. Just as we proved Fermat's rule, we must prove why a Mersenne number can only be prime if its exponent is prime. We will assume the opposite. Imagine the exponent n is a composite number, meaning it can be factored into two smaller integers, a and b. We substitute this composite exponent back into the expression, giving us 2 to the power of a times b minus 1. Using exponent rules, we rewrite this as 2 to the a all raised to the power of b minus 1. Then we introduce a standard algebraic identity for the difference of two powers. Continuing our derivation, we apply the identity. By substituting 2 to the power of a in place of x, we can see how our Mersenne number breaks apart. The equation clearly shows that 2 to the power of a minus 1 is a clean factor of our original number. Because A is strictly greater than 1, this factor is greater than 1, meaning the original number is composite. Therefore, to prevent this factorization from happening, the exponent cannot have any factors at all. This gives us our final result. The exponent itself must be a prime number. So we have proven the rules for both families of numbers. This brings us to a visual comparison. On screen is a graph illustrating why finding these primes is so incredibly difficult. The horizontal axis represents our index or exponent, and the vertical axis represents the resulting value on a logarithmic scale. The solid blue line shows Fermat numbers, which explode in size almost immediately due to the double exponent. The dashed red line shows Mersenne numbers. While they grow slightly slower, they still follow a massive exponential curve. This visualizes why checking these numbers by hand became impossible so quickly in history. This exponential growth we just saw leads us to an important question. Why do we still care about finding these massive numbers today? The search for massive primes is no longer just a mathematical curiosity. It is deeply tied to computer science and cryptography. Modern encryption systems, which keep our bank accounts and private messages secure online, rely heavily on the properties of very large prime numbers. Furthermore, a global collaborative project called GIMPS uses the idle processing power of thousands of computers worldwide to hunt for new Mersenne primes. Whenever a new largest known prime number is discovered in the news, it is almost always a Mersenne prime. Let us summarize the key takeaways from our lecture. We explored two historical attempts to find a reliable formula for generating prime numbers. Fermi numbers take the form of 2 raised to a power of 2 plus 1, but ultimately only the first 5 are known to be prime. Mersenne numbers take the form of 2 to the power of p minus 1, where the exponent p must be prime. While they do not always produce primes, they remain our most successful method for discovering the largest prime numbers in the universe. You now understand the foundations of Fermi and Mersenne primes. Great work today.